Alrighty, class. So continuing on from the last thing that we actually had, we were talking about more probability. Now, when we talk about probability, we have a few different things. For example, we have independent events and we have dependent events. Now, the distinction between them, we had started learning about that type of idea in approximately grade 8, but we for sure talked about independent events and dependent events in grade 9, grade 10, and grade 11, especially when we start talking about science. But overall, the idea behind independent events are so there's no impact on each other. So examples of that would be like rolling a dice and picking a card from a deck. There's absolutely no impact on the other. At the same time, that would be same as rolling two different dice, as long as they don't hit each other. But we usually make a few specific assumptions in there. Now, where that changes is when we start talking about dependent events. So obviously, a dependent event would be there is an impact on each other. Examples of that will be, let's say, you draw a card, then you draw another. So where conditional probability comes in, it's the probability of dependent events. All right. Now we are given two formulas about that. So the probability of A and B happening, again, remembering that this is the intersection typically used to notate the word and, is the probability of one event happening multiplied, that is, multiplied by the probability of B, and this line here is the word for, well, it has the phrasing of given. So the probability of B, given that A has already happened. So for example, my probably favorite example is using a deck of cards. What's the probability of drawing a king, given that the first one is a 7 of hearts? Now, just a simple manipulation of this formula, the probability of B given A would equal the probability of A and B happening divided by the probability of A. And that is a slight typo in here. That should be a capital. And all of those different things are notated down here. So we start talking about a few different things. Please make sure you pause at any point in time if you are unsure of things. But we're going to circle the correct answer. So would each of these result in a dependent event? Drawing an item without replacement does or does not result in dependent events. Or drawing an item and then replacing it does or does not result in dependent events. Again, we talk about dependent. We talk about having an impact on each other. So if you draw an item and you do not replace it, that for sure does have some kind of dependence on each other. You draw one item out of a bag, the next item is going to be impacted from there. Now, if we draw an item and then replace it, it would not result in dependent events. For example, if we had a bag of marbles, well, you draw one red marble. In the first situation, you don't replace that red marble. Well, now the probability of getting a red marble has decreased for the second item. But for this one, if we replace that red marble, it would be an independent event. So it does not result in dependent. Our first example talks about some computer chips. Okay, awesome, I did fix that thing. Now, a computer manufacturer knows that in a box of 100 chips, 3 will be defective. Jocelyn draws 2 chips at random from a box of 100 chips. Determine the probability that Jocelyn will draw 2 defective chips. So if we talk about a tree diagram, we can talk about different situations. For example, the first draw, sorry, let me just change color. First draw, well, it could be good. Well, what's the probability of the first one being good? Well, if 3 are defective, there'd be 97 out of the 100, that would be good. Or that first draw could come out with a bad situation. Now, what's the probability of the first one being bad? Well, that's going to be 3 out of 100. The second draw, if we know that the first one's good, well, what's the probability of the second one being good? If we know it's good, there's only going to be 96 good ones left, but there'll be 99 left in the box. Yes, in the box. If we know the first one's good, the second one could potentially be bad. So if we know that there's 97 that are good, we know that there's 3 that are bad, and there'd only be 99 left in the box. On the other side, if we know that the first one is bad, we could have the second chip being good. There are still 97 chips left that are good in the box. And there'd only be 99 left in. Now there's a potential that you could draw a bad chip and then another bad chip. In that case, 2 would be bad out of a possible 99. So if we want to find out the probability that Jocelyn will draw 2 defective chips, well, the probability that the probability that the first one is defective is 3 out of 100. Kind of just ignored this little line. I fixed it in my Word document, but I think it might have printed weird. Now, the probability of the second one being defective, given that the first one's already defective, well, that's 2 out of 99. If we want to find out the probability of the first one being defective and, again, this intersection being the symbol for and, the second one being defective, we'd have to take the 2 probabilities and multiply them together. Meaning 2 out of 100 multiplied by 2 out of 99. Now, of course, I absolutely love things being fractions. At the same time, I like them being in reduced fractions. I can reduce my 100 and my 2. And I think I might have to do this quickly. Then we can reduce our 3 and 99 being 1 and 33. And therefore, everything will be reduced. By the time that we get to foundations 30, we know that 1 multiplied by 1 is 1. And we can use our calculator if you don't already know that 50 times 33 is 1,650. Please reduce every one of your fractions. It makes things a lot easier. At the same time, it makes it just easier to read. Because if we're looking at this, if we're looking at this situation, that fraction, I'm just going to type it out. Not 1,000, sorry. That does not even look like a 1. Oh, that's because I typed I. 1 out of 1,650 draws would have both chips defective. That's what that's meaning. If we tie that back to our section 1, let's just move that up slightly. The odds of the first one being defective, or sorry, that both of them would be defective, would be 1 to 1,649. Right. Continuing on. Nathan asked Riel to choose a number between 1 and 40, and then say one fact about the number. Riel says that the number he chose is a multiple of 4. Determine the probability that the number is also a multiple of 6. So if we use our Venn diagram, saying that our union, sorry, not union, that our universal set is all the numbers from 1 to 40, we can say, sorry, I'm just having a little bit of difficulties here. This entire first circle could be all of our multiples of 4 from 1 to 40. Circle here, B, will be all the numbers, all the multiples of 6 from 1 to 40, and therefore, all of this intersection here would be a intersection with B. So how many are numbers from 1 to 40 that are multiples of 4 and multiples of 6? I'm going to quickly do this, and if you need to take a pause, absolutely do whenever you need to do it. So by filling everything in the inside of the Venn diagram, the numbers 4, 8, 16, 20, 28, 32, and 40 would be multiples of 4. 6, 18, 30 would be multiples of 6, but 12, 24, and 36 would be multiple of 4 and a multiple of 6. If I fill in the rest of my Venn diagram, I can see that all of these numbers in green would be numbers that would not be multiples of 4 or multiples of 6. So if I go back to the formula back on that first page, probability of B given A would be the probability of A and B happening, dividing by the probability of A happening. So I'm just going to write that down. So let's go through this. What's the probability of a number being a multiple of 4 and a multiple of 6? If we go to our Venn diagram, we can see that it's 3. But it's 3 out of what? So I'm just going to change my color. How many total numbers are there? 40. Now we're going to be dividing that by the probability of A. Well, that's the probability of something being a multiple of 4. So there's a total of 10 numbers there. Now, of course, I like writing things out like this, just so you can see, but at the same time, remembering that this division is a division, which means we have 3 out of 40 divided by 10 out of 40. It's a fantastic thing that by grade 12, we know how to divide fractions. Different phrasing, multiplied by the reciprocal, multiplied by the reciprocal after the obelus, multiplied by the reciprocal. I've seen and heard a whole bunch of them, but no matter what, still comes out as 3 out of 10. So where is that number actually coming from? What is the probability of it being a multiple of 6, given that it's a multiple of 4? We could also potentially read that straight from our Venn diagram. This part right here, given that it's a multiple of 4, well, how many things are a multiple of 4? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. how many are a multiple of 6 as well? 1, 2, 3. So there's 3 out of these 10 that are a multiple of 6, given that it's already a multiple of 4. I don't have a huge focus on this formula. I just like you to know that we can just manipulate formulas to get what we need, because the probability of A and B happening does equal our probability of A happening multiplied by the probability of B, given that A has already happened. And then our last couple examples. According to a survey, 91% of Canadians own a cell phone. Of these people, 42% have a smartphone. Determine to the nearest percent the probability that any Canadian you met during the month in which a survey was conducted would have a smartphone. So we want to define a few things. Yeah, so in case you're not up to date with the oldest technology, to be a cell phone does not mean that you have a smartphone. It just doesn't happen, because absolutely there are people that have cell phones that are not smartphones. Yes, and I am old enough to know that, or to have owned a Nokia, the actual brick that would not break. Alrighty, so let's substitute our values in. So according to the survey, 91% of Canadians own a cell phone. So the probability that someone owns a cell phone is 91%. Of course, when we were dealing with percent, it's always nicest to write things as a decimal. Now, of these people, that is probably your key terminology in this question. You need to make sure you do read questions. Of these people, 42% have a smartphone. So what's the probability of having a smartphone given that it's a cell phone? 42%. So if we want to try and find out what is the probability of cell phone and smartphone happening, it'd be the probability of our cell phone happening multiplied by the probability of smartphone, given that a cell phone has already happened. So 0.91 multiplied by 0.42. And that comes out as 0.3822. Of course, if we're dealing with something with percents, it sometimes is very beneficial to put things back to a percent. Now, before you go into things and you start thinking, oh, what does this actually mean? Like, aren't all smartphones cell phones? Like, not really. Because if you look at any kind of carrier, there are absolutely people who just have data. Well, that doesn't mean that you have a cell phone. Maybe using cell towers, you may be using the connectivity, but having that actual ability to make the phone call without that Wi-Fi or technology of connectivity, well, you got to be careful. It's not really the same. So there's your little bit of technology information. Okay. Last question. For example, Hillary is a coach of a junior ultimate team. When we talk about ultimate, we talk about ultimate frisbee. Very fun game, very fast pace, but you have to make sure that you have a very good environment to do that. So based on the team's record, it has a 60% chance of winning on calm days and a 70% chance of winning on windy days. Tomorrow, there's a 40% chance of high wins. There are no ties in ultimate. What is the probability that Hillary's team will win tomorrow? Well, for us to properly do this, we need to set ourselves up into a tree diagram. We have two situations happening. Now we can do our tree diagram like this, or we could potentially do it down. Either way would still work. I like working with it horizontally just for the fact that we're dealing with a multiplication of ideas, which means that we can then do things further. So if Hillary's team has a 60% chance of winning on calm days and a 70% chance of winning on windy days, but there's a 40% chance of high winds. Well, we have three percentages, and all that we've ever had to do is multiply two. No, you don't have to multiply 60% by 70% by 40%. That's not how we're going to be doing this. You have to deal with the different situations. Either we can have no wind, or we can have wind. We have a 40% chance of high winds. So 40% is 0.4. If there's a 40% chance of high winds, it means that there's a 60% chance of no wind. All right? After that, we can deal with the other two situations. If there's no wind, what's a percent that she's going to win? She has a 60% chance of winning on calm days. Well, if it's a calm day, so again, this is no wind, does mean that it's a calm day, she could still potentially lose. Meaning, there is a 40% chance of losing. If it's windy, even though it's only 40% chance of high winds, she could win 70% of the time. But of course, if she can win 70% of the time, she could also lose 30% of the time. Here's a big question. What is the probability that Hillary's team will win? We have two situations here. We can have no wind and have a win, or we could have wind and we could win. I'm just going to move that slightly down just to have the numbers in there. We're going to still take our multiplication. 0.6 by 0.6 is 0.36. 0.4 by 0.7 is 0.28. So if there's a 36% chance of her winning when there's no wind, there's a 28% chance of winning when there is wind. Now that's of course dealing with the total, not talking about just 36% chance. Talking about, well, if there's a 40% chance of high winds, we're just trying to deal with some situations. Say 36% add 28% should come out as 64%. And therefore, in total, that means that Hillary's team has a 64% chance of winning tomorrow. Good chances. So meaning she'll win approximately 2/3 of the time. Good percentage and fantastic things to do. Now, some good practice questions are absolutely in your Foundations 12 textbook. I have some other supplemental stuff if you do need it.